Hello, we're going to go ahead and move on to section 2.5 of force diagrams on the inclined plane. Again, if you haven't read the book, please do so. Chapters 4 and 5 in Coletta. This is going to be related to the homework 5 in sapling for 2D forces if you're in Physics 121, and homework 8 in sapling if you're in Physics 111. And this is going to be more on related to Lab 7. So with problems where there is something on the inclined plane, there is a kind of a trick, okay? And it makes the mathematics easier. And we've learned up until now to keep the y direction always pointed up and down and the x direction always left and right. But in a way, I've always learned that you want to make sure that the x direction part of the coordinate system is always parallel to the motion. It makes it a lot easier. So the only way to do that is to actually twist our entire coordinate system. So now, if we're in an inclined plane that is pointed up and to the right, our x direction part of the coordinate system is also going to be pointed up and to the right, and the y direction part will always be perpendicular to that. So that'll be twisted up and to the left. And if the inclined plane is pointed up and to the left, then we want the x direction part of the coordinate system to be doing the same. And as always, the y direction is going to be perpendicular to that. So we're always going to, no matter what, we're always keeping the y direction part of the coordinate system perpendicular to the x direction. We're just twisting the x direction part of the coordinate system to be parallel to the surface of the inclined plane. No matter what, though, we want to make sure that just because we twist the coordinate plane doesn't mean that our weight vector m times g is going to be twisted too. That will always be pointed straight down towards the center of the Earth. So what we're going to do is we're going to go through the steps on what we need to do to draw a force diagram and how this will affect our forces. And mostly it's going to be affecting mg. Most of the time it's going to be affecting just mg. If you haven't done so, well, maybe later on, go ahead to the Khan Academy video, and it's inclined planes, frictions. It's the first video that comes up in the supplementary videos, and he does a great job explaining how the inclined plane theta here is the same theta here. And I could show you that too. I just really like his explanation. All right. So in order for me to teach this to you, what we're going to do is do this practice problem. And we have a box. It's just sitting on a rough inclined plane. It is not moving. In this case, we're going to call G 10 meters per second squared, just to make it simple. The inclined plane makes an angle theta. It makes an angle to the horizontal of 30 degrees. So theta is 30 degrees. And we want to know what the magnitude of the normal force is compared to the weight of the object. So that's probably just going to be the y direction stuff, but we're going to go ahead and do everything. So let's go ahead and do this problem, and we're going to we're going to go through the steps. And it's very important to start off by drawing our coordinate system. So I'm going to go ahead and just draw a coordinate system really quickly on this actual problem. There's no fillable area, so again, we're going to have to go to our comments area to pull up that bar with our tools in the PDF. And then you go ahead and push this little arrow to push this back. Oops. And now we have all of our tools. We have our text box, we have our drawing tool, we have our shapes. So I'm going to use a line to indicate the coordinate system here. Okay. And the x direction is going to be parallel to the plane right here. I'm going to label that. I'm going to label the positive x direction part of the coordinate system. I'm doing this for a reason, and I'll show you in a second why I'm doing it. And here's the y direction stuff. Let me go ahead and do the y direction. It's going to be perpendicular to the x direction. And I'm going to label the positive y. It's not necessarily important to label the negative y. Some people do that. I like to do that in my actual physical classes. But in here, I don't want to make this picture too busy. So now that we have our coordinate system, okay, so I'm going to copy these objects right here that I've drawn. I'm just holding down the control button, copy it. I'm going to go over here. I'm going to paste it right. See if it'll allow me to move everything together. Nope. Oh, yep. It allowed me to move that coordinate system. And the reason why I did that on the picture over here is I just want to be as accurate as I possibly can. So now what I'm going to do is I'm going to try to see if I could change the color of this. Let me see if I could do that. Hold on one second. So now that I've got my coordinate system over here, and notice that my color is red. If you need to change the color of the ink, if you click on this, a little red dot will open up, and you can go to the tool and change that to black to change the color to black. And the reason why I'm going to do that is I'm going to be drawing forces on there, and I want to use a different color than the coordinate system. And in the shapes, that will probably also be in red. You're going to want to click on the shapes, on the arrow, and this, it was originally set to red. So if I want to go to this, you click on the arrow again, and it'll be in red. Change the fills to black, change the border to black, and now I'm going to be able to draw black arrows. All right, let's go ahead and draw our forces. So what is physically touching and interacting? What forces are interacting with the block? And what objects are physically touching the block? All right, well, the Earth is going to be pulling down on the block, so it's going to have a weight vector. And I'm going to go ahead and draw that. Weight vector down. I want to make sure that that is black and that border is black. And notice I drew that arrow really long. It's going to be easier if you make the weight vector really long in this. And I'm going to go ahead and label that mg. I'm not going to give it a sign yet because mg is going to end up being broken up into cosines and sines. So let me go ahead and put that right here. Oops, I probably should have labeled that, made that text box black too. There we go. So I'm going to go ahead and pull that MG and make the text box. Oh, don't want to fill that in. Just want the border to be black. Oh, I don't have to have a border. Well, that's pretty cool. Just learned something. All right. And there we go. I forgot to actually draw a line for the 30 degrees. So there you go. And we're going to go ahead and label this 30 degrees. So this is 30 degrees right there. Yep, made it a little bit too small. All right. So here's our object right here, and it's going to have a line right to there. So, so now that we have mg, we're going to wait to break that up into the sines and cosines. All right, let's draw the other forces. Well, it's sitting on a plane, an inclined plane, so it's going to have a normal force, and that normal force is going to be pointed perpendicular to the surface, and it's going to be holding it up. So in this case, the normal force is actually going to be pointed up and to the right, perpendicular to the inclined plane. Okay. I'm going to label that the normal force, and since that is pointing in the positive y direction and it's along the coordinate system, I'm going to go ahead and name it as such. Okay. And friction is going to be working on this. Now the object isn't moving, so the object is not moving. But if it were to begin to slip, I'm going to use a border here. If it were to begin to slip, it would be sliding down the plane. Okay. And so, since it's not moving, okay, if it were moving, it would be sliding down the plane because there's no other forces working on it other than the normal force, mg, and friction. And the reason why I'm talking about this, I need to think about the direction of the friction vector. So it wants to slide down the plane, but something is holding it up, okay? And it would want to slide in this direction, but the object is not moving. So we know the object is not moving. I'm just going to put v is equal to 0. This sounds a little bit weird, and I put an arrow there. But the object is not moving, okay? But if it were to move, it'd be moving down the plane. That means the friction vector is pointed up the plane. Okay, and the friction vector is going to be parallel to the surface. Okay, and that is going to be pointed in the negative x direction. Okay, so negative x direction. It's going to be black, so negative x direction. So negative mu sub k times the normal force. Don't forget to include the normal force. Too many people forget to put on the normal force. They just put mu sub k. It's mu sub k times the normal force. Mu sub k is a coefficient and has no force to it. It's just a number. So this is pointed in the negative x direction. All right. Now, here we are. We have our basic force diagram. And I just want to be careful here. I'm going to also indicate. So it is not moving. 0. And it has no acceleration on it. All right, here's our basic force diagram. Now, if you notice, this makes, this is our inclined plane. And if you watch the Khan Academy video later on, they'll show you what I'm about to show you here. I'm going to go ahead and grab this. And I'm going to show you how this is going to be our angle 30 degrees. So I'm going to snip this right here. Actually, let me go ahead and not do that right just yet. I'm going to remove this, and I'm going to remove this, and remove this, and I'll snip it in a second. Go ahead and snip this. And I'm going to show you how 30 degrees is right there. All right, I put that back, and now I'm going to go to here. All right, here is where we're at. All right, let's go ahead and put our coordinate system here. So if you notice right here, this is theta. And if that's theta and this is 90 degrees, this has to be 90 minus theta. Okay, so that's 90 minus theta right there. Okay, and I'm just going to put this right here. That's the angle, 90 degrees. So anyways, let's go ahead and draw a line. I'm going to copy, I'm just going to cut this off real quick right here. And this is now a new triangle. Even though this is 90 degrees and it looks bigger, this is actually 90 minus theta as well. And then if that's 90 minus theta and that's theta, then this will then be 90 degrees of this smaller triangle. Okay? So we have a mini triangle of this whole thing. Now what I'm going to do is I'm going to draw another vector, another line right through this segment right here. And this line is going to be perpendicular to the surface right here at this point. Okay? And that means that this whole area right here is going to be 90 degrees. But we know this part of the angle is 90 minus theta, but we know this entire area is 90 degrees. So if this is 90 minus theta and this whole area is 90 degrees, then that means this is theta right here. That means this small angle right in here between the perpendicular to the surface and this vertical line right here is theta. And that is our mg vector. So going back to our problem, now we can see that that 30 degrees right here, I'm going to copy that, paste that here, is also this is our 30 degrees. Okay? Now I'm going to go ahead and I'm going to draw, I'm going to go ahead and break up this vector in terms of sine and cosine, because this is now a diagonal. It's not pointing along our red coordinate system. Okay? So I am going to grab a shape, and I'm going to grab a vector, and that is pointing down in this direction. Okay? Now, I've done this a lot. And actually, before I do that, let me stop for a second. I've done this a lot, and I can recognize that this is actually the triangle that we're drawing. And this is often hard for a lot of students to do that. And so one of the tricks I've learned is I'm just going to grab this vector right here and overlay it on top of our system. So one of the things I've learned to be able to easily recognize the triangle is let the x direction coordinate system sink below. And if you do, and when it keeps sinking down and it's still parallel to the surface, let it keep sinking down so it reaches the tip of that vector mg. Having a hard time drawing it. Here we go. We'll lengthen this, make it a little bit longer. And so now you could see a little triangle that is emerging. Okay? So that is going to be how we're going to be breaking up mg, which is diagonal to our coordinate system. It's going to be pointing down. So I'm going to draw a down vector. And then it's going to be pointing to the right. Okay. And there you have it. What we're going to do now is I move the mg to be easily recognizable as a hypotenuse. This is the y direction side of mg. This is the x direction side of mg. Okay, so let's go ahead and figure out what those are. And this is a hypotenuse. We have a hypotenuse and we have an angle 30 degrees. So this side right here is adjacent to the angle 30 degrees. So that is going to be that is going to be pointing in the negative y direction, so it's negative mg, and it's going to be, since this side is adjacent to the angle 30 degrees, so it's going to be mg cosine of 30 degrees. Now let's get that smaller so we can see that. Move this so it's easy to recognize. So this is pointing down in the negative y direction. Negative y is down here. Negative y is down here. Now let's go ahead and do the opposite sign. The horizontal direction, which is along the x direction coordinate system, this one is opposite the angle 30 degrees. And even though it's pointing down the ramp, it's pointing in the positive x direction. So this is going to be a positive mg sine of 30 degrees. Okay? All right. What I want you to do right now is I want you to sum the forces in the x direction and sum the forces in the y direction for this twisted coordinate system. Go ahead and pause the video and try that now. All right, here we go. Right, so let's do the x direction first. So I'm going to recognize, I want to make sure that I can see how many horizontal forces are here. It's going to be a little bit harder for me because this horizontal is now along the coordinate, is along the plane, the inclined plane. Well, I could see I have one vector pointed up the plane, parallel to the plane surface, and I have another pointed down the plane. Okay, and I've got those directions labeled. So what I'm going to do is I'm going to copy that over here. I'm going to make this text larger so it's easier for us to look at. I see a negative mu sub k times the normal force pointed in the negative x direction. So that's going to be negative mu sub k, and I should use u, and that k is going to be subbed times the normal force. Oops, gotta turn that off. And I have a positive mg sine of 30 degrees. I want to make this larger than I normally do. Okay. And that's equal to mass times acceleration in the x direction. However, it is not accelerating in the x direction or the y direction. So this is going to be 0 newtons. Okay. So I've got everything accounted for. Now I'm going to go ahead and do the y direction. Well, the y direction looks like I have only two vectors, a normal force up and mg cosine of 30 degrees down. So I'm going to put positive capital N minus mg cosine of 30 degrees. Now let's go ahead and adjust the size of our text box. And that is going to be equal to, so I've only got those two forces acting on it, and that is going to be equal to mass times the acceleration in the y direction. The y direction goes along, the y direction acceleration goes along with the y direction, and it is not accelerating off the plane or into the plane. So that is going to be 0. Oops. Sorry about that. So that is also going to be 0 newtons. Okay. And now we could ask a number of questions. What would be the coefficient of friction, for example? You would have to solve this for n, and then plug it into here. So there's a lot of things that we could do here. But what they're asking here in the actual problem is, what is the what is the normal force compared to the weight of the object? So in this case, the normal force is not equal to the weight of the object. Okay, it looks like when we bring, so I'm going to go ahead and do this. So let's go ahead and compare the normal force to what we have right here. So we have a normal force pointed up. We have mg cosine of 30 degrees down, and that's equal to 0. Well, if you bring the normal force, if you bring mg cosine of theta onto the other side, so you add that to both sides, what you find out is that the normal force is equal to mg cosine of 30 degrees, which is not equal to the weight of the object. Mg cosine of 30 degrees is less than the weight of the object. So to answer this question, what we would say is that mg is greater than the normal force. And so there's the problem. That's the answer to our problem. mg is greater than the normal force because n is equal to mg cosine of 30 degrees, which is less than the weight of the object, mg. All right, I hope you enjoyed this. All right, let's move on to another practice problem. This is the exact same problem as before, except now the triangle is twisted the opposite direction. All right, so we're going to try to use the same method that we did before, but we're going to go a little bit faster. Right? So I'm going to start off by drawing a line. I'm going to draw my coordinate system through the inclined plane. I'm going to label it positive y. Make it red. Let me put this down here so I could make this red. this smaller. All right. And now we're going to draw another line to represent the coordinate system for the x direction, which is perpendicular to the y direction. All right. Move this over here. Change this to an x. And there we go. There's our coordinate system. I'm going to take all of that and bring it over to here. And the reason why I did that again is I want to make sure I'm as accurate as I possibly can. All right. Again, same problem as before. This object is going to have a weight vector on it. Okay, so it's going to have a weight vector on it. It's going to have a normal force acting on it. And it's going to have a frictional force acting on it. Okay, so go ahead and draw that force diagram now, given this coordinate system. Go ahead and hit pause, please. All right, I hope you've done your force diagram. So let's go ahead and draw ours. Draw an arrow pointed down. I'm going to draw the weight of the object. Again, I'm going to make this longer than normal. I'm going to label this mg, and I'll make sure it's black to be consistent with my forces. Okay. Connect it there. Cool. Go ahead and I'm going to draw the normal force. The normal force should be perpendicular to the surface. And in this case, it's pointing in the positive y direction again. And since it's pointing along the coordinate system, I can now give it a plus and a minus. In this case, it's pointing in the positive y direction, so I'm going to call that a plus. Okay. Now I'm going to go ahead and draw the frictional force. If this block were allowed to slip and it was allowed to move, it would slide down the ramp. That means friction has to be pushing it up the ramp, opposite the direction of what the velocity vector would be if it were allowed to slide. So I'm going to draw another force vector. And this is a frictional force. And the frictional force in this case is going to be pointed in the positive x direction. So positive mu k normal force. Okay. I forgot to draw my, let me do something real quick. I need to draw where my 30 degrees is. My theta is 30 degrees. It's going to be right there. Okay. And again, the angle 30 degrees is the angle 30 degrees to the actual inclined plane makes an angle 30 degrees between mg and the y direction coordinate system. So just like before, we're going to try to recognize the triangle. And I'm going to just copy this real quick. So I'm copying the x direction coordinate system. And just like before, I'm going to let it sink down so that we can see where it lies. And that makes our triangle. And so this right here, this 30 degrees, is actually going to be right here. Let me just see if I could do something real quick. see if I can make it no fill. Oops. Okay. Let me see if I could do that again. Make this 0 opacity. Nope, that didn't work. Well, I'll keep moving on. So this is 30 degrees right here. And we have our triangle. Notice that MG is not pointing along the coordinate system. So we're going to have to break that up. We're going to have to, MG is the hypotenuse. We have the angle 30 degrees. And so what we're going to have to do is we're going to have to create our triangle. Well, this part of the triangle, you can pointing down. And we're going to have another part of the triangle pointed to the right. I mean to the left. Okay. So it's pointing, this MG is a hypotenuse, is pointing down in the negative y direction and also down the ramp in the negative x direction. Okay. So now let's label it. This side right here is adjacent to 30 degrees, so it is going to be pointed in the negative y direction. Okay. And that'll be negative mg, and it's adjacent to the 30 degrees. I want to make sure that opacity is up to 100%. There you go. That means this other side right here, pointing in the negative x direction, is opposite the angle 30 degrees. So that has to be the sine. And it's pointing in the negative x direction. So there we have it. There's our force diagram for problem number 2. Go ahead and sum the forces in the x and y direction, and we'll go ahead and attempt to answer the question. Pause the video now. All right, let's go ahead and sum the forces in the x and y direction. In the x direction, I see 2 horizontal vectors pointing along the x direction coordinate system, negative mg sine of 30 degrees and positive mu sub k times the normal force. So we have positive mu sub k times the normal force, right? And that k is a little sub, minus mg sine of 30 degrees. Got to remember to expand my text box in this. And that's equal to mass times acceleration in the x direction, but as stated in the problem, the object is not moving. So that mass times acceleration in the x direction is actually going to be equal to 0 newtons. Oops, forgot my 30 degrees there. In the y direction, I see a normal force pointed up. I see a negative mg cosine of 30 degrees pointed down. And that's the only 2 vertical forces. Normal force up, negative mg cosine of 30 degrees pointed down. That's equal to mass times acceleration in the y direction, which is also equal to 0 newtons. It is not accelerating, it is not speeding up or slowing down on or off the ramp. It's not moving. Okay. So we need to, again, to compare the normal force to the total weight of the object. Well, in order to do that, we're going to go ahead and use this y direction equation. All right. normal force minus mg cosine of 30 degrees is equal to 0. Okay? What we find out is that the normal force, if we add mg cosine of 30 degrees of both sides, we find out the normal force is equal to mg cosine of 30 degrees. Same thing as before. And what that tells me is that since the normal force is equal to mg cosine of 30 degrees, that means mg is greater than the normal force, because mg cosine of 30 degrees is less than mg. So we get the same answer as before. So the next part of the notes, I put in a problem by Knight where he's got an example problem of a car being towed uphill. And he approaches it a little bit differently, but essentially he is doing a very similar process, just in a slightly different way. So you have a car being towed uphill with the car has a weight of 15,000 newtons. Okay, so mg, that's not the mass of the object, that's mg is equal to 15,000 newtons. It's being towed up and at an angle of 20 degrees up a slope at a constant velocity. So it's not accelerating, so the sum of forces in the x and y direction applying Newton's second law is going to be equal to 0. There is no net force. The tow rope is rated to pull at 6,000 Newton max tension. Will it break? So they're not saying that the tow rope is 6,000 newtons. They said if it exceeds 6,000 newtons, if it reaches or exceeds 6,000 newtons, it will break. Okay? So here's the problem. So we're going to be towing a car uphill. Since it's rolling, we're not going to really worry about friction in this case. So he drew his force diagram. You've got the rope towing it uphill. So he's got his coordinate system. Again, it's twisted, right? Just like our first practice problem. The normal force is pointed up in the positive y direction. The rope T is pointed in the positive x direction. mg, or 15,000 newtons, is pointing down, but it makes an angle theta to that y coordinate system, and theta in this case is 20 degrees, right? He's kind of showing how he's going to sum the forces here, and he's assigning the forces there. But here are his x and y direction. He's got an x direction sum of forces, and he's got a y direction sum of forces. And he basically, even though he summed both the forces in the x and y direction, again, if there's no friction, you're really not going to be needing the normal force. Oftentimes, you're not going to be needing the normal force. If there's no acceleration in the y direction, there's no friction. Sometimes, in this case, you're not going to need the y direction sum of forces, only the x direction. And when he compared that, he solved for t is equal to mg sine of 20 degrees. Okay, so the weight was pulling down the ramp, down to the left. The tension is pulling it up the ramp, up and to the right, the positive x direction, and that's 5,100 newtons. So therefore, it does not exceed 6,000 newtons, and the rope does not break. We're going to be doing a similar problem that they just did, but I'm going to break it down step by step. And what I want you to do is go ahead and attempt this problem right here. And I want you to draw a force diagram right here. In this case, you've got a box sitting on an inclined plane, pointing it in the opposite direction than it was in the last problem. Okay. It's on a frictionless inclined plane, so there is no friction. It's a 2 kilogram box. The angle is 30 degrees. Again, we're just going to call G as 10 meters per second squared. And we want to know what the tension in the string is, just like the last problem that Knight just did. So go ahead and do a force diagram right here. Okay? Pause the video, please. All right, we're back. I'm going to go ahead and, just like I did in the last couple problems, I'm going to go ahead and grab a line. I'm going to draw my coordinate system over here because it's going to help me. And I'm going to label this. Going to make sure I use red for the positive y direction. I'm going to go ahead and draw a line for the x direction coordinate system, I should say. And I'm going to label that positive x. Grab that guy. All right. The reason why I'm going to do that is I need this coordinate system for my force diagram, which I'm going to do right here. And I want to make sure I remember to grab my angle, which is 30 degrees. All right, 30 degrees. Let's make this a little bit smaller. All right, now let's go ahead and begin drawing our force diagram. Just like we always do, we're going to try to identify all the forces acting on our object. So this block is sitting on an inclined plane. It's going to be pulling, it's going to have a weight vector straight down. The inclined plane is going to be pushing it at a perpendicular to the surface in the positive y direction. And the rope is going to be pulling it up the plane in the negative x direction. All right, let's go ahead and draw the force diagram. So I've got a weight vector down. I'm going to draw that weight vector larger than what it normally would be because I want to be able to use that to draw my triangle. And I want to label that mg. I'm going to make this bigger, and I'm going to make it black to be consistent. There we go. The angle 30 degrees is actually right here as well. Okay. I'm going to go ahead and do the easy part real quick. I'm going to draw my normal force. My normal force, is going to be pointed in the positive y direction. And since it's pointed in the positive y direction, I'm going to label it a positive n. Now there's a rope pulling it, and it's pulling it in the negative x direction or up the ramp. And that is going to be, since it's pulling it in the negative x direction, it's going to be a negative t. And there you go. Now, that is almost completely done. Let's go ahead and break the mg up so it's consistent with our coordinate system. So mg is going to be the hypotenuse, 30 degrees is going to be the angle. I want to be able to easily recognize the triangle, so I'm going to go ahead and copy the x direction coordinate system, let it sink down till where it reaches the vector head. Of mg. And I'm going to make this a little bit longer so it's easy to see the triangle that makes around 30 degrees. All right, let's go ahead and make that diagonal, which is a hypotenuse mg and the angle 30 degrees. You have it's pointing down and to the right if we twist our coordinate system. and it's also got another vector that's going to be pointed to the right. So the vector pointed down in the negative y direction, that is pointing in the negative y direction, so it's negative, and it's going to be the hypotenuse cosine of 30 degrees. Oops. And the x direction, horizontal vector is pointing in the positive x direction. So that's going to be positive mg sine of 30 degrees. And there is our force diagram. What I want you to do is go ahead and sum the forces up in the x direction and y direction. So let's go ahead and sum the forces up in the x direction right here. And we'll do another one and sum the forces up in the y direction. And then we'll use these two sums of forces. Let me just make sure this is going to be nice and clean. We'll use these two sums of forces to answer the question, what is the tension in the string? So go ahead and pause the video in a second and sum the forces in the x and y direction. So pause it now, please. All right, and we're back. This might get in the way of our sum of forces. I'm going to make it smaller. So I'm going to go ahead and sum the forces in the x direction. And I see one force, negative t, that's pointed in the negative x direction. I see an mg sine of 30 degrees is pointed in the positive x direction. Okay, and we have to remember this is not moving, nor is it accelerating. So negative t plus mg sine of 30 degrees let's go ahead and make this bigger. And that's equal to mass times acceleration in the x direction. But that is, since it's not moving or accelerating, there is no acceleration in the x direction, so that is 0. We don't have to do this, but let's go ahead and do the same thing and sum the forces in the y direction. In y direction, we have two vectors. We have positive n pointed in the positive y direction, and we have negative mg cosine of 30 degrees pointed in the negative y direction. So I'm going to put a positive n, and that's going to be equal to negative mg cosine of 30 degrees. And again, that's equal to mass times acceleration in the y direction, but since it's not moving nor accelerating, that is equal to 0 newtons. All right, let's try to solve the problem. In order to solve this problem, we're going to compare tension. We're going to use the x direction forces to compare the tension in the string to, and we just actually have to solve what the tension in the string is. So we're going to use this. So I'm going to bring the tension, well actually I'm going to rewrite this so it looks a little bit cleaner, plus mg sine of 30 degrees, and that is equal to 0. All right. Now I'm going to add the tension to both sides, and what I have is mg sine of 30 degrees is going to be equal to the tension. I just brought the tension onto the other side. And so what we have now is we have now we have a comparison of tension to mg sine of 30 degrees. And tension is equal to mg sine of 30 degrees So if this is a 2 kilogram box, then we know that the tension is going to be equal to 2 kilograms times 10, which is meters per second squared. That's gravity. So 2 kilograms times gravity, the gravitational acceleration, meters per second squared, times sine of 30 degrees. So let's grab our calculator. I'm going to go ahead and do this. 2 kilograms times 10 meters per second is 20 newtons. And I'm going to multiply this by the sine. Okay, let's grab a function. So 30 degrees, and I'm going to go ahead and take the sine of that, which is 0.5. So, which is 10. So what that means is the tension force is equal to 10 newtons. And that's our answer. And there you go. There is this problem. Finishing up lecture 2.5 and forces all together, I want you to attempt the lecture tutorials. So the lecture tutorials, again, there's a fillable area. Make sure you type in your name. You're going to go ahead and use the drawing tool, the shapes in the drawing tool, just like I showed you how, to draw on the force diagram right here on the block. And I want you to go ahead and use the text box to fill in the text of the sum of forces for your force diagram. Please do that for this block problem as well as this other block on ramp problem, except here you're going to have to make 2 force diagrams, one for the block, which is going to have a twisted coordinate system, and one for the rock, which is a hanging mass. Okay? And this block is sliding down the incline while slowing down. So you're also going to have to sum the forces in the x and y direction on both of those. The related homework problems that are really close to these is 8.01 in Physics 111 and 5.01 in Physics 121, 8.04, 5.04, 8.02, 5.02. So please do these 3 problems in coordination with this part of the activity. It'll help you out. Thank you.